So I finally want to attack this issue of the pressure, and here's the beginning. You see? There's not enough pressure. I told you everything is a pressure. Yeah. So here's the internal energy that I mentioned before. And if you look formally, what you get is the relation between this internal energy. So the internal energy is given here. And if you look formally, what I mean formally? So basically, we know that we have an underlying equation. Right? So this is essentially, if you like, the equation for the empirical distribution that we assume it has a limit, the moments has limit. So I skip that, I make everything formal, and I take this Vlasov equation, and I look at the moments. Now, if I take the moment, which has to do with the V minus U squared, then you get the equation upstairs. The equation tells us what is the dynamics for the internal energy. The dynamics for the internal energy, as you can see up there, is given in terms of some mysterious Q. What is the Q? Q is the cubic moment of F, because there is always the problem of closure, which has to do with the heat, but I will put it aside because I don't really care. The really important thing is that the following term appears. This is the trace of the pressure matrix times the gradient of U. Gradient of U is the matrix, the stress tensor, DUI, dxj. So we take this product of matrices, we take the trace, and formally we get this equality, which is balanced essentially by the alignment term. So it's there, it's just formally there. And then out of the blue, I will define to have an entropic pressure if instead of equality, I get inequality. This is my definition. Of course, you might say, well, it doesn't mean anything, it's just some definition, so who cares? But bear with me a second and you'll see why I define it in this manner. It really not only makes sense, it's the correct definition. So E is the internal energy, Q is an arbitrary smooth, I will call it heat flux, I really do not care, but I really care about having this inner inequality. Of course, the difference between equality and inequality is huge because I allowed anything that satisfies this inequality. For example, zero. The zero is internal energy, is fine. But namely, there is no pressure. Okay, so why do I need this inequality? So now let me walk back and I'll show you what's going on. Because once I have this inequality, so I give you as an example what happens in the canonical case of fluid dynamics, for those of you who are familiar, because of course this all comes from fluid dynamics. So in the case that the pressure is a scalar pressure, denoted here by little p, so the pressure and the internal energy are related in the manner that is described up there, and then we get the usual equation for the pressure and the usual inequality for the specific entropy, which is written here. When I say the usual, it's surprising because actually the inequality should be reversed. But this is a different story that I don't have time now to cover that. Why we have this inequality in this direction? Because here the order is not, the disorder is not increasing, it is decreasing. Okay, anyhow, this is the definition that I impose. So I'll write it here. It's important that rho E T plus the gradient of something plus the plus the trace of the pressure times the gradient of U is less equal than whatever the alignment gives me. So this is the definition. And now I do the following calculation. Here's the inequality. And now I take the mass equation, it's written here. I take this mass equation. I multiply this by U squared over 2. And then I take the momentum equation. This is the momentum equation, and I dot it with U, the whole equation. And I add the 2. So this is something completely algebraic. It has nothing to do with anything. And lo and behold, when you do that, you get what is written up there. And the only thing I want to look is minus the trace of P grad U. This is a mistake. It should be the trace of grad PU. That's the only thing I did this exercise. So this is completely formal. If you take the mass equation, any system with the mass equation and the momentum equation which has anything on the right-hand side, if you do this algebraic manipulation, you will... I see. Now I understand what's going on. I couldn't figure it out. So this was without battery. Okay, that's okay. It is my problem. So any system, you will get there minus the trace of the grad PU. It is an algebraic thing, and that's the only thing I would like to look at. The reason is all the other perfect derivatives will disappear. The only thing I have to cope with is how do I have access to the trace of the P grad U when I don't know the pressure? And that's exactly the purpose of my definition. Because now I take the definition of the internal energy in line 1, I add it to line 3, and lo and behold, what I get is I get a statement for the totality of the rho U squared, which is the kinetic energy, and the internal energy, which I call the total energy, which is rho capital E written up there. This is this term. This term. And now I get that the total energy is not increasing and it's dictated by whatever comes on the right-hand side. In our case, it has to do with the alignment. How do we know that? It's exactly the same trick that I used before and that Yao mentioned before. When you look at this term, it's not a negative, it's not coercive. But actually when you integrate, if you integrate again against not just the x prime, but the x, and then you do the symmetry, you will get a negative term. And the key element here is that the non-differentiable term disappears. So now I have a statement that the total energy is not increasing. But we know that we are not interested in the total energy because this is the wrong statement in the sense that I cannot deduce anything from that. Here are fluctuations. You see, U minus U prime is a fluctuation of velocity. Internal energy is fluctuation of velocities, right? The kinetic velocity. There is no pressure anymore. It disappears. The price I have to pay is I don't know what to do with the energy. But we know that the rate of change of the energy is the same thing as the rate of change of the velocity fluctuations. And that's exactly what is going on here. So I will use the fact that there is a decay here of the energy. So I will use the fact that ddt of the integral of the energy will be the integral of U minus U prime squared plus E prime dx when I integrate this twice, and I have to put here rho and rho prime, dx prime and dx. Now, of course, they are not the same, but the rate of change is the same. That's what I've shown before in the discrete case, and that's what will happen now. So it's the big structure is to compare fluctuations with the amount of the decay of these fluctuations, and the only difference here and there is, of course, what we have here as the kernel. It's always repeating itself. But we pay attention to one more thing. Since this is decreasing, we know that the integral in time of this quantity is finite. So let me write this as well, because eventually this is the only thing I will use, namely that the time integral of the double integral in space of phi of x and x prime of U prime minus U. I don't care really about the internal energy, but let's take it, that this quantity is bounded by a constant, and the constant has to do with the initial energy. Okay, so now we have all the ingredients which are will suffice to show what is the large time behavior. And you ask yourself, so where is the pressure? Where does the pressure disappear to? Well, it disappears exactly at this stage. Here's the pressure, in the definition of the internal energy, and here's the pressure there. I add the two, and the pressure disappears. And then you say, well, you have a pressure here. I don't care because I'm going to integrate this, and the pressure disappears. So I get a very little information. I get that the total, this quantity is called entropy, is bounded, and I get that the rate of change of the energy here, which is the energy fluctuation, is dictated by the energy fluctuation here. Okay. So before we do that, I would like to make one more step, which is important. I would like to introduce a new notion of alignment, and the notion of alignment, which I call P alignment, is written here. What you can see is I introduce an amplitude for the difference of velocities, which has to do with the 2p minus 2 power of Vj minus Vi. This is in absolute value. This is a scalar number. So let me tell you a few comments about that. Number one, if p equals to 1, this is what we had before. 1. Number two, this is an odd quantity. And that's all we needed for everything in the discussion we had before. Oddness. And everything will work out. So it satisfied the oddness property. Number three, if we had before graph Laplacian, this is called graph P Laplacian, which appears now a lot in machine learning and so forth. So it is appropriate to introduce it here. And number four, why did I introduce this? Well, we will see later on that in a very natural manner, it is the right quantity to look at. And basically what it means is that the alignment is stronger when the Vj and Vi, the difference of velocities, is far away. But when the velocities are close to be aligned, then the intensity of alignment decreases. So this is fundamentally different behavior than the usual Gronwell exponential decay, blah, blah, blah. And indeed, we have here the 2p Laplacians, which appears in neural networks, and so forth and so on. And when we take this, we get the same hydrodynamic description. The only difference is, well, you can see that this intensity appears there. That's the only difference, and I call it P alignment. As we shall see, this P alignment plays a critical role later on in the large time behavior. In fact, not only is it much richer, in some sense I will try to convince you that this is the right model for alignment, if I may say so. You will see why. Okay. Fine. So now I come into this business of P alignment, which actually highlights many things, but I thought instead of doing it on the slides, I have to do something on the board with detailed information. So, yeah, let me do it here. Let us try to see what can we say about this P alignment and why the P alignment is I claim, is important. So we have this kind of model. And we would like to study the energy, not the energy balance, in fact, the balance of fluctuation for this P alignment. Let's try to look at it in the usual way. And the usual way is that we take the inner product with Vi, and we sum over all the i's, and then we scale by 1 over n. This is what I have done before when p equals to 1. And we got the usual exponential decay and so forth, blah, blah, blah. What do we get in this case? Well, what we get on the left-hand side is, so this is essentially the rate of change of the energy. And we know by now that the rate of change of the energy is the same as the rate of change of the energy fluctuation. This is what I'm driving at. So I have to sum over I and j, and I scale it by 1 over n squared. This is exactly what I've done before. So that's fine. That's what we have on the left-hand side. But what do we have on the right-hand side? Well, on the right-hand side, we get 1 over n, the sum j, phi ij, vi minus vj to the power 2p minus 2, and then we take the inner product of vj minus vi times vi. And the only thing that we need is oddness. Why? Because now, of course, we change the indices. We have to sum it over I and j, the I from here and the j from there. and then we get phi ij, and then we get vi minus vj 2p minus 2. This does not change. And now we get vi minus vj times vj. And we take the average. But this is exactly what we have done before. And we know what will be the answer, because we know that this will be now coercive, this will be negative, just with this prefactor, just as we had before. So now we will get minus 1. By the way, I divided it by n, so I have to rescale it by n here. And then when you take the average, you get 1 minus 2n squared, and then you get sum phi ij, vi minus vj 2p minus 2, and from here we get vi minus vj squared. Voila! That's exactly why I scale it with p. We get this. And of course, it's a negative quantity. So how these fluctuations of order 2p relate to the fluctuation which are quadratic? Well, they just work in the right direction if you use Holder inequality. So the way we do it, this is minus 1 over 2n squared. Now I have to work it out. This is the sum of phi ij 1 over p, vi minus vj squared. Okay, so now let's see. If we take the sum of phi ij 1 over p, vi minus vj squared, and we take the pth power of this quantity. So this will be less equal, because we want the reverse inequality, than the sum of phi ij to the power 1, vi minus vj to the power 2p, and then we have the sum of 1, and then this is to the power p prime, so this means p over p prime. P prime is p over p minus 1. And therefore, what is my problem? My problem is to find a lower bound for this quantity. A lower bound for this quantity is written here. A lower bound for this quantity is given by this power, okay, to the power p. And I have to divide here, so this number is n squared. P prime is exactly the power p minus 1. So we have to divide here by n squared to the power p minus 1. And so I get here minus 1, 2n. The 2 and the 2p minus 2 gives me here 2 to the power p. And then I get the sum, and then I get phi ij 1 over p, vi minus vj squared, everything to the power p, ij, and therefore it will be best if we will put here 1 over n squared, like so. Why I want 1 over n squared here? Because I have 1 over n squared here. In fact, to be correct, I have 2 over there, so let's put here the 2. I will be pedantic, and then this will be replaced by minus p to the 2 to the p minus 1. And lo and behold, what we get now is the following statement, that these are the energy fluctuations, and the energy fluctuations are less equal. I cannot say that they are equal because I used here Holder inequality. They are less equal than it's not exactly the energy fluctuation. Again, we have these coefficients that I have to pull out. So let me pull out this coefficient, and I would say that this is less equal than minus 2 to the p minus 1. I will pull out the phi, and then what is phi? Phi I will assume is a function of xi minus xj. So let me pull out phi of the distance, the diameter, where the diameter is the max of xi minus xj. It's a function of time. And when I pull this out with the 1 over p and p, I'm left with delta E. So if I call this delta E, the fluctuation of velocities, I end up with the statement that the time derivative of the fluctuation are less equal than minus, and then up to a constant which is just some power of 2, phi of d of t times delta E to the power p. This is not Gronwell inequality. This is Riccati's inequality, and the behavior of this inequality is fundamentally different. The reason is that the decay in this case is fundamentally different. There is no exponential decay anymore, there is polynomial decay. So all of a sudden we move to a completely different arena, which goes to tell me that exactly what we will see here. So let me continue now with the slides. So basically this is the calculation in the discrete case. In the hydrodynamic case, it becomes even slightly more complicated. But you see, in the hydrodynamic case, I need somehow the kinetic closure, which I do not have. What I do is, I do in the hydrodynamic case, I do this kind of polarization and I try to estimate essentially using Holder inequality. And when I do all these steps, which are pretty delicate, I would say, essentially what I get is that the rate of change, this is this last line, the rate of change of the energy, i.e. energy fluctuation, has to do with the fluctuation weighted with the phi. That's exactly what I had here on the board. But how I connect the two? So I know that this is energy fluctuation, the same rate. What about the fluctuation here? I have to pull out the phi outside, and I pull out the phi by taking the phi at the diameter, which is the minimal value. And that's exactly what is done here. So we get the entropy bound, and basically we get the dissipation term, and eventually here is the energy fluctuation. The rate of change of the energy fluctuation is the same as the energy, and now we have to solve Riccati's equation. So this is Riccati's equation that we have to solve. And where do we get this second eigenvalue? When we pull out phi ij to the 1 over p, we know that we can pull out the minimal value, but we are smarter. We know that we can pull out the Fiedler number. So it's the same mechanism as before. I pull out the Fiedler number, and here is the Fiedler number, the second eigenvalue of whatever the Laplacian, the spectral gap of some Laplacian operator is. And that's the end of it. So we know that in general, the fluctuation of the energy has to do with the pth power of the fluctuation of the energy. And it means that there are two cases. And the two cases now tell me that if the Fiedler number is non-integrable, then the fluctuation of the velocity will go to zero and the pressure will go to zero. So without knowing even what the pressure is, the pressure will go to be monokinetic, which is remarkable because I know that for large time, we recover really the monokinetic case. Okay, but what is the behavior here? So here's the theorem. So now we have to be specific. Let's assume that the phi is actually dominated from below by a function which is essentially a metric. I just want it to be very general, but I assume that I have a metric envelope below, and I will have to assume something, how fast this decays. And also I will have to assume how fast the diameter may grow. So there is a competition here because eventually the spectral gap is bounded from below by k of the diameter. So what is really going on is that there is a decay of the interaction as a function of the distance, and at the same time the distance may grow. And the combination that really matters is k composed with the diameter. So the question is how this behaves as a function of time. Okay. Okay. So here is the statement. Let's assume. So let me summarize now all the pieces. They're not complicated, but I like to point out what is the essential aspect. Let's assume that we have a strong solution which consists of a density, velocity, and a pressure that I have no idea what it is. Let's assume that this is an entropic solution in the sense I mentioned before. And now we assume something about the behavior of the interaction. The interaction decays with, say, power eta. So this is how fast it goes to zero. Let's also assume that the diameter of our blob may grow in time with power gamma. So now there's a competition between eta and gamma. Why? Because we have to make sure that eta times gamma is less than 1. If eta times gamma is less than 1, then the integral of this composition will be infinite. And indeed, we will conclude that if p equal to 1, then the fluctuation decays exponentially fast. And if p greater than 1, they decay polynomially in terms of p. So this general theorem, I can just tell you that this is pretty surprising, at least for me, because this theorem applies to anything with any pressure, which is entropic, without knowing anything. It simply comes from the fact that there is a balance of fluctuations here. And of course, we need still one more very important thing. The question is, what is the dispersion? How fast, if at all, the flock can disperse? Hopefully they do not, but we do not know it ahead of time. Okay. Okay, so here's the statement. If eta gamma is less than 1, then we know that the velocity will approach the initial average and the internal energy goes to 0, and this is the flocking that we are looking for. Then we know everything. So everything that we want to do is just to justify this if. Is it true that the product eta times gamma is less than 1? Now, what is eta? Again, eta is given to us. It's about the profile of the tail. Okay, let me write this because now I write in red. These are important statements. So we have now the following. We now zero in on really what matters in this general alignment dynamics. The first statement is that we have a communication kernel, and it's up to a constant greater than 1 plus the distance between x and x prime to a power which I called eta. Okay? So this is something that is dictated, and I will assume that eta is given to me. In particular, this rules out short-range kernels. So if you have a short-range kernel, then I don't know what to do. So I will assume that there is a long-range kernel, and the long-range kernel has to do only with the tail. Okay? Good. The second thing is that I need, so this is 1. 2, I have to assume something about the dispersion. Let's say it grows with a power of gamma, and gamma is any number which is greater or equal than 0. And then I need that eta gamma is less than 1. If eta gamma less than 1, then I can tell you everything independent of the pressure. So when I look at this, the only thing which remains to be done is to address what is the gamma. Namely, if at all, is the flock really dispersed and grows or not? That's the only question that remains to be done, independent of the pressure. Okay. So, let's take the case eta equal to 0. Eta is very good. Eta equal to 0 is when we have a constant. That's what I mentioned at the beginning. When eta equal to 0, there's no problem, right? It's just relaxation. I know. We are really interested in the case that eta is greater than 0. Now, when eta is greater than 0, then it's not clear what will happen with the gamma. There is a tension here between the interactions and the possibility of things to spread out. Okay. In particular, there's a big question, is it true that gamma equal to 0? Gamma equal to 0 means that the diameter is simply bounded by a constant. And this is what I assumed when I started the first lecture, that the diameter is bounded by a constant. It sounds like a innocent assumption, but it turns out to be the critical assumption. If you know that the diameter is bounded by a constant, you are done. So that's the reason I just put it in an innocent way, but actually this is the key element. Okay. So let's take the monokinetic case, because now we can talk about any pressure. In fact, the monokinetic case covers almost all the literature that was done in the last 10 to 15 years. And the only question is, of course, is it true? What about the gamma? So the statement is that in this case, when there is no pressure, and if eta is less equal than 1, then the diameter of the D is bounded. And therefore, the fluctuation decay to zero exponentially, blah, blah, blah. If you want to see the proof, I mean, there are many proofs of that. I mean, starting with Cooker and Smale. But let me tell you what is the essence. The essence is that the fluctuation of the velocities are bounded. So this is detailed proof that one has to show that in this case that the fluctuation of the velocities are bounded, and therefore the diameter is bounded by the fluctuation of velocities. The diameter may grow linearly, and therefore the fluctuation of the energy decays with fractional exponential, as I mentioned essentially yesterday. And this implies the fluctuation of the velocities decays also with exponential, fractional exponential order, and in particular, the time integral is finite. So when I integrate the fluctuation, I get that the diameter remains bounded and I'm done. So this kind of bootstrap argument is not the most effective proof, but it's most revealing proof. So the key element is, do we know anything about the velocities? And it essentially enforces us to get into the equation and see what do we know about the equation. So far, I didn't tell you anything about the equation. I'm telling you when there is no pressure, then the fluctuation of velocities are pointwise bounded. Okay. Now, how do I know that the fluctuations are bounded? Because there is a maximum principle. Why do we have a maximum principle? We have a maximum principle because these are scalar equations. They are completely decoupled. The pressure is the only quantity that connects all the components. Okay, let me show you an example how things are not simple, because otherwise one gets the feeling that everything is so easy here. Let's take the following example. So here's an example when there is no pressure. And essentially what we have here, this is the momentum equation. I normalize it by the density, I took it out. And this is the alignment. But with one trick. Now the alignment has a matrix coefficient. Where do I get the matrix coefficient? Well, I told you when you actually do the formal derivation from anticipation, you do not get a scalar communication. What you really get is the Hessian of some underlying potential, and this Hessian is a matrix. Now, if this is a matrix, now these are not scalar equations, right? Because even if you look at the scalar component, they are all interconnected because of this matrix. And here's a simple question. Show that for these systems of equations, the velocity remains uniformly bounded. It's a very simple question. Is it true that for this simple equation, if this was a scalar, then essentially you get here a maximum principle because it's just disconnected transport. But if you get a system here, then it's not trivial. How do you show that you get a maximum principle, not a maximum principle, a uniform bound on the velocity? And if you get a uniform bound on the velocity, the problem is done. This is exactly where we are right now. Just prove that the support, this is ST, is the support of the density, which is not written here because it is driven by the mass equation, right? Here's the density. Show that the support, the diameter of the support, is bounded by a constant. And this follows if you can show that the L infinity of the velocity is bounded by a constant. So everything is reduced to that point. This is at the heart of matter. This is it. Now I cleaned everything. The question is, how do you prove it? Let me just... Let me just show you how it goes here. Anyone has an idea how to show it? So the point is we take this equation and we dot it with U, and then we get an equation, pointwise equation for the local energy at that point. Yeah. Yeah. So we get a transport equation, but constrained by the quantity on the right-hand side. So this is the fluctuation, this is the matrix x prime, and this is the velocity. And now we use polarization. And the polarization tells us that I write it as this, I can write as the integral. Okay, now I have to pay attention. I can write it as the integral of, minus 1/2, okay, minus 1/2 u prime minus u phi u prime minus u minus 1/2 the integral, no, there is no integral, yes, there is integral, the integral of u phi u, and then plus 1/2 the integral of u prime phi u prime. So essentially, I take this integral, this integrand, and I decompose it into 3 terms, 1, 2, and 3. And the 3 terms essentially is called polarization decomposition. This is just an identity. You can check that what is the sum of these 3 integrand is the integrand on the top. The point is that we do know one thing about this matrix phi. It is positive definite. It is the Hessian of convex potential. And I will assume that this matrix is bounded from above by some constant, let's call it A, times the identity matrix. So I will assume that this communication kernel is bounded from above and it is not negative, which essentially means that this is negative, and the only thing that remains is the integral of u prime phi u prime, and then we have to integrate against rho prime dx prime. Okay. So this means that this is less equal than up to a constant. Well, there is some constant here which I do not take into account, and then I get u prime squared, and then I get rho prime here, and then I integrate dx prime. But this quantity is the energy, and the energy is bounded. So this is bounded by a constant, depending on the initial data. So we conclude, therefore, that we get an equation of this form: dt u squared over 2 plus u grad u squared over 2. Here is a transport equation, and this is less equal up to a constant. This is less equal, so let's see. This term is negative, this term is negative, this is a constant, so I have to be careful in one thing here. Just a second. I have to be careful in, yes, when I pulled out this phi, I have to see what is this constant. So what I get outside is up to a constant 1 plus the diameter to the power minus eta, 1 to the diameter minus eta, and then I get here plus u squared times the mass plus a constant. So basically I get a transport equation for u squared, which is constrained by something that goes to 0 plus a constant. So this means that the u time t, the L infinity norm of that, is bounded. And if you integrate that, what you get essentially is up to a constant. This behaves like 1 over t to the power 3/2 at the beginning. Yeah, exactly. Right. Well, this does not mean that the velocity is bounded. So what one does is now one has to assume something about the diameter here. Let's assume that the diameter behaves like 1 plus t over gamma. We don't know what the gamma is. If you plug here that this is like 1 over t over gamma and you integrate this equation, the result will be that u of t is bounded by 1 over t to the power, let me check this, 1 over t to the power to the power, okay, because we have to integrate that. So to the power u of t is bounded by, just a second, because we get d dot t is bounded by the L infinity of u, and this is bounded by 1 plus t to the power, okay, so just a second, this will imply, okay, so this I did not, this I just copied, okay, so we get here some number here, delta, and once we integrate, so this delta depends on gamma. When we integrate that, then we get delta depend on gamma, and this implies eventually that d of t is bounded by a plus b t to the power gamma prime, when gamma prime is 1 plus eta gamma divided by 2. So the key idea is, let's assume that the diameter expands in certain rate. We use this equation. We plug this expansion rate into this equation. We control the velocity. Once we control the velocity, we control the diameter. We find what is the controlled diameter, and we find out that it can grow at a rate which is gamma prime. So this means we started with gamma, we get gamma prime. So this means that we can implement that again. And this is the canonical bootstrap argument, and the final conclusion is therefore that the solution will be the fixed point theorem for this mapping gamma to gamma prime. And the fixed point result for that gives us that the gamma fixed point is given by 2 divided by 2 minus eta. And therefore the statement here will be, which is written there, whenever eta is less than 2/3, then gamma eta is less than 2 over 2 minus eta. And this is the final result that we get for this system, that there is no expansion and therefore there is flocking for any eta which is less than 2/3, which is pretty remarkable because in the scalar case we get eta less than 1. Okay, so this is the kind of argument that one needs to do here, but let me now move to the, I have 15 minutes. Let me move now to the case when there is a pressure. When there is a pressure, I still owe you a statement, what happens to the diameter? In fact, what happens to the diameter, I need point-wise estimate on the velocity. So in some sense, this is a very demanding statement. How can I estimate point-wise the velocity when I know nothing about the pressure? In fact, this is a canonical issue in all non-linear PDEs. But here we can do something. So let me tell you what's going on. Here's the idea. The idea is, let's take a kernel which has a singular head. It will have the right heavy tail that we are familiar with when eta is less than 1, you know that. But now I don't look at the tail, I look at the head. And I would like to focus my attention on singular head. So my tail, my kernel will look something like this. It is singular here, but it does not go like that. Then all of a sudden it slows down, and then here it's heavy tail, and here it's singular. You see, if you continue with the singularity there of order d plus 2sp for any s which is greater than 2 over p, then the tail for the first line is not good enough. So I have to slow down the tail while I connect it to the singular head. This is the kind of kernels that I would like to look at. And the claim is that for this kind of kernels, which emphasize the local interactions, and they still have the right tail, then in general, we will have, independent of the pressure, we will have flocking. The reason is why. So this is an interesting aspect. Let me show you why. What is really going on there is that when you get this singular kernel, you can see that here is the P alignment, here is the kernel that we are discussing, and here is the tail, which I'm really not interested in. I'm really interested now in what happens in the interaction when x prime is close to x. Of course, this is a singular kernel, so this is the principal value. In fact, this is a fractional Laplacian of order 2p. That's exactly how it works. This is a fractional Laplacian. And you can see that this fractional Laplacian, this P and the degree P here are connected. This is the reason I introduce it. And in a minute, you will see that the relation that d over 2p is less than 1 will be necessary. So everything fits together. Okay, another thing that you will see, that if p equal to 1, and you have to believe me that this red constraint is unfortunately essential, if p equal to 1, I need d over 2 to be less than 1. So when p equal to 1, which I did the whole theory from A to Z, and at the end I got the result for only one-dimensional equations. And I was very disappointed. This is exactly how it worked out. Because I needed d to be less than 2, strictly less than 2, not less equal. So I really debated for a long time what to do in order to move the theory for more than one dimension. Until I really proposed this p alignment, and then when p is, let's say, 2, then it allows the dimension to, p equals 3/2 or less than 3/2, it allows to move to 2 dimensions. So let's see how it works. Why the p alignment is so important? Well, this is the model, and essentially it has to do with fractional Laplacian and so forth. And the important thing here is that what was written before the entropy, we get the entropy bound which is written here. When we do the integration, we get that u minus u prime to the power 2p. This is the kernel. This is rho times rho prime. This is bounded by the initial data. When we integrate in time, this is the entropy. So we get a statement here. This is an important statement. It tells us, without knowing anything, that for this model, when you look at this integral, something about the average derivative of u is bounded. To be precise, what we are told here is that the WS2p norm of u to the power 2p is bounded, if we assume that we are staying away now from vacuum, which I'll take for granted. The important thing here is that this statement doesn't tell us anything which is pointwise. It tells us that on the average, when we integrate in time, on the average, then the velocity cannot be too large. So this is an average statement on the fractional derivative of the velocity, but this will be enough because we have bounded entropy. And the final step is to use the Gagliardo-Nirenberg inequality, and it tells us if you control the velocity on the average, you can control it pointwise. So here's the statement about pointwise control of the velocity, namely the difference of the fluctuation of the velocities between points x and x prime is proportional to x minus x prime of order s minus theta times the average bound that we have here. And what is this s and theta? Well, this is true for any s which is greater than theta as long as d over 2p is less than 1. This is exactly why we introduced that. So this is the tunnel through which the average control of velocity is controlling the pointwise fluctuation of the velocities, and that's exactly what is needed. Except I do not control this, I control it in time. I need this integral in time to be controlled. But that's exactly what is needed, what is provided, because we know that the rate of change of the diameter is bounded by the fluctuation of velocities, and therefore we have to integrate this Gagliardo-Nirenberg, and when we integrate it in time, we get the time integral of the 2pth power of this Sobolev norm, fractional order, times the integral of 1 to the right order, and we end up with a time growth of the diameter which is no more than some constant given in terms of p, theta, and s. So this is the first time where we have access to pointwise statement on the diameter. But this is not the end of it. We know that in this business we have to use bootstrap argument. And that's exactly what we have done. We started with this growth of gamma p, and we iterated that. And we iterated this statement, and I want to emphasize, this is true for any entropic pressure. There is no closure and there is no maximum principle. And when we iterate that, this is essentially how we do it. We take into account that once we know that the diameter grows like gamma, it implies that the fluctuation decay at certain rate. That's exactly as I've shown before. The fluctuation decays at certain rate, so it means that there is another property of the velocity and therefore the diameter, and therefore I do the bootstrap argument, and I conclude that the diameter is less than gamma prime, and this gamma prime now is 0, as long as P is less than 3/2. And that's the end of the story. So this is a statement that for any pressure, the alignment will drive everything to flocking as long as P is less than 3/2. And I debated a long time about these 3/2. And in this case, when P is between 1 and 3/2, it turns out that the fluctuation decays in this optimal rate, which is given by this polynomial rate. And there is a problem here because if you remember, I told you that I started with this P alignment because I needed this condition that D over 2P must be less than 1. Right? Because I have to put an S there, which is the amount of smoothness. So if I took P equal to 1, it means that the dimension is less than 2, namely has to be 1 dimension. And now I come to the point when P is less than 3/2. Let's take 3/2. We found out that D is less than 3. Namely, D is either 1 or 2. So I was able to prove now that for all 1 and 2 dimensional, the flocking behavior independent of the pressure. And the question is there really the 3 dimensions so fundamental? At the beginning, I was absolutely convinced that I can break it, and now I'm not sure. I don't know if there's something really essential in these 3/2. And as you can see, I wrote up there, the borderline case is when in the P alignment P equal 3/2, it means that we take the U prime minus U with the order 1 of U prime minus U, and this seems to be a critical. In the pressure case, in the non-pressure case, it is not clear. And so the P alignment seems to be the right concept to give the right behavior, but it's stuck in 2 dimensions and nothing more. Okay, so when P is greater than 3/2, yes, I can get that the diameter may grow at a certain constrained rate, but I cannot drive it to be 0. So I get some fixed point gamma star, but this fixed point is positive and not less than 0. Okay, so this was a long story about alignment and pressure and pushing the boundaries of the theory to have pressure. And now what? Now we come back to multi-species. If you remember before in multi-species, I said, oh, the pressure is not important. Why? Because I didn't know how to handle, but now I do. So now we come to multi-species and we remember everything that we have done about multi-species. And here's the story. Now, when we have the mass equation and we have the momentum equation, and now we have P alpha, which are the pressures for species alpha. And now I do not want to push the pressure because I know what I'm doing. And here are the alignments, the usual thing that we discussed yesterday. Okay. And as usual, we assume that the phi alpha beta, these kind of different interactions, they are bounded from below by some metric kernel, K alpha beta, and we have to look at, of course, the weighted Laplacian, which are given here, and we know that the Fiedler number of this weighted Laplacian will dictate everything. So the question is, of course, to zero in, where is the beef? Where can we say something which is really meaningful and not just, okay. So the answer is, we know what the answer is. We know that if the graph is connected, so the graph connectivity means that the lambda 2 of the weighted Laplacian should decay at most of order eta. And if there is a controlled dispersion of order gamma, well, if eta and gamma is less than 1, then we are done. That's the story. Now the question is, how do I know that the gamma is, I need control on gamma, I need pointwise estimate on the diameter, I need pointwise estimate on the velocities. And we are back into the game. Where I'm going to get the pointwise estimate on the velocities. But here we can do it, and it's quite interesting. You see, the alignment term in the singular case, we will assume that the interaction of each species with itself is based on singular kernel. The interaction between different species, I really do not care. The tail will take care of that. But the interaction of each species with itself will assume to take a singular kernel, a singular behavior like that. And this singular behavior, why do I need this singular behavior? The only reason is because I'm going to integrate it in time, just as before. And when I'm going to integrate in time, I will control the Sobolev norm of fractional order of the velocities. And just as before, I will get the theorem that if we have entropic pressures, and if eta gamma is less than 1, gamma p is given in this in this fashion, then the diameter may grow at a certain contained rate. So the question, of course, is, well, can you make this gamma star to be 0 to show that there is a finite flock which does not expand? And I was unable to. So the best result that we were able to get so far is this thing, because the bootstrap argument that we did with one flock did not work out with multi-flock. So there are still open questions here. What happens in more than 2 dimensions, and what happens when there are multi-species, and how to do the bootstrap argument. Clearly, the bootstrap argument can be refined, but I don't know how to do it. And at a certain point, I had to stop. And this is indeed a good point to stop about this whole discussion about multiscales and alignment, and to thank you.